So moin, this video is part of the scientific Python programming lecture or tutorial at the University of Bremen. And in this session, I would like to introduce you to the basics, how to plot things in Python, especially how to visualize scientific data in Python with the help of the matplotlib package. As always, we will do our exercises in the Ubuntu virtual machine, which we have set up for this course. And basically, I already have started the virtual machine, and then I already started the Jupyter notebook in which we will work for this tutorial. The slides you can always find at the same place as always. So this is basically still part of chapter 5, the file IO and plotting with matplotlib. So this is basically one set of slides for both topics, and then we are basically starting here from the plotting data with matplotlib part. The previous part was covered in the previous video. Now, when we want to plot plot things in Python, we have to first decide where we want to see the result of the plots, and basically those are two different components. So this is the so-called matplotlib render engines, and then basically now we will work here in the IPython notebook. So we will visualize, or the Jupyter notebook, we will visualize the things here, but also there are other options. You can, for example, let Python to pop up a window and show the graph there, or you can even save it in a PDF file. We'll see also example for all those cases during this session. Yes. Otherwise, what you should also know is that in the plotting, there are the different ways how to treat the plotting capabilities of the so-called matplotlib package in Python. There's a simplified interface, which is called pyplot interface, and this is what we will use, is because it gives you a very easy and access to many features. But if you want to make more complicated things, more detailed things, then you have also a fully object-oriented interface to all the things which this plotting routine is creating. So all the axes, all the graphs, all the curves, and you can set up very detailed properties. I won't treat that into this lecture, but this is something you should be aware, and in case you need very specific manipulation of those things, you can look it up in the documentation. Anyway, in this tutorial I will give you only a start, because there's a very good tutorial in the internet about the plotting capabilities of Python. I will show that later. So basically I only show you the very first basics so that you can start. Okay, so let's have a look. We would like to plot something like this. So this is the purpose of the exercise of today. So basically we would like to plot a sine and a cosine function in one plot using some data, which are basically data which represents the sine and the cosine functions, so sampling of those functions. We would like to plot it with different line styles. We would like to have some labels, some legends which are placed at a certain location, and we would have maybe axes in a certain way. And this is exactly what we want to do. And in order to show you that it's quite simple in Python, I would like to say, and we will go line by line for this example, but I would like to show you that this is the piece of code which produces the figure which we have seen before. So it's not very complicated, but there are a few things we have to deal with. But if you have a very quick look at that, okay, here we are importing some modules, okay, that we know already. Then here we are creating something which is maybe it's called x. Then we are which is maybe some x values we would try to represent. Then we are here basically creating some y values, some function values, and then we are just here using some plots, and maybe here we are telling here Python that it should create a legend, and then we are showing the graph. So basically that's it. And of course now we would like to treat it point by point or line by line. So let's go through this example. And the first thing we have to do is, because we would like to see the plots here within the notebook, within the matplotlib notebook, and therefore we have to tell the program that they should show it within the notebook, and that's the option. This is the magical option matplotlib, and we can just write inline. And this basically doesn't do anything else. Just make sure that if we are using matplotlib within the Jupyter notebook, the figures will appear in the Jupyter notebook, which is quite handy and quite nice. And then we will need two packages. Basically, we will need the NumPy packages, which we are already using anyway for many purposes. For example, in order to create the arrays or manipulate arrays. And additionally to that, we will import the matplotlib package. And within the matplotlib package, we are choosing the sap package, which is called pyplot. And this is the simplified interface which I was mentioning before. and we will basically use the access via this simplified interface. And this is basically in order not to have to type matplotlib.pyplot in the front of every command, we are just abbreviating as PLT. So let's do that. So basically we are just importing our modules, numpy as np, and we are importing numpy dot no, sorry, this is just matplotlib, not numpy, matplotlib dot pyplot. You see that here also you can use the tab if you want to extend or auto basically auto extend module names, and in order to make it short we will just call it plt like plot. So we have to import those two modules, which we did, and now we want to start to create our graph. And basically the way how we are creating very often graphs or figures for scientific data is that we have some x values and corresponding y values, and we tell Python or the graphical package to basically draw a line connecting the points of each point which we specified as x and y value, and just connecting them. And this is exactly what we will do now. And first of all, we have to decide what kind of x points they would have to have, and we will use the linspace package of the NumPy program. This generates basically linearly spaced points, so points with the same distance between same separation between each point. And there we only have to say in which range we would like to generate these points. And as you see here, basically we are going from 0 to 4 pi. So basically, let's say we want to calculate points from 0 to 4 pi. In order not to have to calculate pi, we will just take the constant pi from the numpy module. You see, this is if you make the tab for the file name completion, then you see that np.pi exists. So we are taking just 4 times pi. And then it will generate points in that range, and we have to say how many points, and we will just generate 200 points within that range. And in contrast to the range function, which we usually use to generate an integer range, this function, if you use linspace, it will basically also contain the both endpoints. So we will have a point at 0, and we will have a point at 4 pi. Let's execute that. We can have a look at that, how it looks like. Indeed, the first point in 0, and the last point, if you scroll down, is 12.566, and this is exactly 4 pi, because if you just print the value of 4 pi, you see it's exactly the same thing. So basically it also contains the endpoint. You can also specify not to contain the endpoint if you wish. So basically in theory you could just say endpoint equal false instead, and then the endpoint won't contain, but basically no, we would like to have the endpoint here inside. By the way, if you would like to have a help about a certain function, I had already showed you that you can use the Python built-in function help and then pass np.linspace. That's something which we had already, but basically there's also another way to do that. If you are working in a Jupyter notebook, you can just say a question mark and the function name, and then you immediately get in another window a very nice help which shows the same information, but it's a little bit better because it's not embedded into the notebook, and you can even convert it into a pager, basically in a separate window, and then here you can read the full documentation. And for example, this full documentation, you see that you have an optional bool argument which is called endpoint, and basically this endpoint tells true, the default is true. If it's true, then basically the last, then the stop point is the last sample point, otherwise the stop point is not included. So if you want to look up here what it is, what the options or the different arguments you can pass to linspace, for example, you can just do that. Okay, so we have now the x points. The second thing which we need are the y points. So basically we would like for every x point have a corresponding y point, let's say the cosine function first. So basically, if we go ahead in the slides, we have generated here now the x functions, and now we want to the x values, and now we want to generate the y values. So basically, we can use the cosine function from the NumPy package. The nice thing with the cosine function from the NumPy package that you can pass an array to this function, and then the array would be applied element-wise. It's called ufunc. So basically, y1 would be an array which contains exactly the cosine values to these x values, and then the second one we are just plotting the sine associated with the variable y2. And now if you, for example, have a look what the shape of y1 is, then it should contain exactly 200 entries. And for example, if you look at the first value, epsilon or y1 0, which is basically the cosine of 0, that should be 1, and indeed that's the case. So it really contains the cosine values. While if you look for the second function y2, it's a sine, of course, for x equals 0, it's 0. So basically with that we have the values which we want to plot, and now basically what we have to do is to indeed to plot them, so basically to visualize them. So how can we do that? Basically we can do that by using the plot commands here, and with the plot commands the usual syntax is that you, or one of the possible syntax, you are specifying the x and the y points. So you are specifying an array which contains all the x points and an array which contains the corresponding y value for each x point. So let's just do that. We just say plot plt.plot, and then we are just for example here plotting x and y1 for example. And then if you do it in Matplotlib within the Jupyter notebook, then it immediately is shown. If you would just use a script and you would just create it in a script, then you could say plot, you would have to say explicitly plot.show. We will also have a look at that in a minute. And basically that would here for you show the cosine function. If you want to also plot the sine function, then you would just be here also make a plot, and again the same x point, but you would take y2 as a function, and then you see that basically it already have chosen a different color for the sine function. The color has been chosen automatically because we didn't say anything about how the color has to be chosen, and then it has been shown. And that's basically the trick. And now what we will do is basically to refine these plot commands in order to manipulate how the output looks like. But before we do that, I would like to show you how it works if you are doing the same thing, but not in an IPython notebook, but in a file. So basically, I will just go to the folder where I'm working now, and I will create with leafpad a Python file. Let's say leafpad, and I will call it just plot.py. Usually you should not use leafpad in order to edit Python code because of the indentation is very important in Python, and we will learn a more complicated editor, the Spider, soon, where you can do big Python projects quite nicely. But for this very simple exercise, I will take leafpad because the only thing I will do, I will just copy paste things from here. So basically I will just copy paste those two lines from here into the leafpad notebook. Of course I forgot the I, just to demonstrate what it does, and then I will just copy this line and these two lines here, and once I did that, finally I want just here the two plot commands, right? And that's it. I don't even want more. That's already the same program what we had before. I'm just saving it and leaving it. And now basically here in the work folder, I will just say Python 3 or Python 3 plot.py, and I will just run it. And then you see that in contrast to the IPython notebook where we had the figure embedded, here we get a figure in a separate window. So basically, and this is why you need the plot.show command at the end, because that would basically trigger the creation of the window, and then it shows you the results. The nice thing with that window, and this is what I wanted to show you, that you can basically manipulate the view. So for example, you can click on the axis here, axis button here, and then if you come with the cursor here in the figure, and then you are pushing the left mouse button, and then here dragging around, then you can basically drag around the curve. If you want to zoom in, you just push the right mouse button and then shift here and there, and then basically if you wish, you can zoom in a certain region or zoom out, depending in which type. If you just up and down would zoom in and out, left and right would also zoom in and out according to the on the x and the y axis respectively. You can also basically zoom out a rectangle if you wish. This is and so on and so on. And if you want to go back to the original view, you can just reset it, and you can also, even if you had subplots, we will see what they are. You could even here manipulate them. So basically here the left and the right, for example, the margins, you could here push, then you see that the margin moves and so on and so on. So basically, if you want to interactively manipulate something, it's quite good. You can do it there, and you can even save the figure in PNG format, for example, or even in EPS or PDF. So there are many things, many formats you can use. So sometimes it's also a nice option to have it in a window. But basically now we want to work here in the Jupyter notebook. I just wanted to show you the other possibility. And now what you would like to do is to refine this graph. So basically there are a few options I would like to, a few refinement I would like to do here. And first of all, I would like to make sure that I specify the colors of the curves and also the line style I would like to change. For example, we want to make, let's say, the cosine curve red, and we would like to add dashed lines. So basically we would say that the color is equal red, let's say, but that works. You see the cosine curve is already red, and then let's say color equal, you can just click blue, but specify explicitly then it's blue for the sine curve. Now the line style, that's the next option. The line style tells you how the curve looks like. For example, if you are using dash dash, then it will be a dashed line, while if you are using for example here line style is equal let's say dash dot, then you would get a dash dot, or if the line style is just a dash, then you would get a continuous line, and so on and so on. So that's already quite nice. We can also specify the line width. If I want to specify the line width, let's say 2.0, then you see that basically the cosine curve got a little bit wider, or let's take 4.0, then it's obvious that the cosine curve is much thicker than the sine curve. And the last thing which I would like to show you is the labeling it, because it would be nice if we had some description what is what, because at the moment in the function it's not clear what is what, but we can have a description. So we can say the label should be just a string cosine x, and here the label should be just a string sine x. And then if you look at that, you see that okay, but nothing changed, because you have to tell pyplot explicitly or matplotlib explicitly to show the legends, and that's just the command plt.legend. And that only means that create a legend, and that means now you see it here, it shows okay the thick red dashed line is cosinus x, while the normal continuous solid line blue is sinus x. I will just decrease the line width to a reasonable width, and I set here the same so that we have exactly the same line with both, and we have these curves. And basically that's it. That already creates this sine and cosine function description, and as I said, we could already set up a little bit the style of the curves. Okay. Now, what else you can do? Okay, you can, for example, instead of showing the figure, you could just save it, save the figure into a file, and this is also a very handy option. So basically, instead of showing it, we could just say plt.savefig, and then as you have seen the slide, basically you have to provide a file name and the format. Basically, the file name would be curves.pdf, and then you would like to make sure that it's saved in PDF format. Actually, if the file name is from the file name, it can guess which format it should be used, and that format is used. So basically, in this case, it's not necessary to do PDF, but if you want to explicit and say, okay, it should be this PDF format. Let's see whether it does. First, let me change to the command line window. This is the folder where I started Jupyter Notebook from, and you see that there are no PDF files here. Okay, and now if I'm executing this here, in theory it was saving the figure. As long as you are working in the Jupyter Notebook, it's also showing the figure, even if you say it only save the figure. But if you are working with the scripts, as I have shown before, then basically it will not show the figure anymore, because plt show is missing. It will just create the file. Now let's have a look at the file. if I'm listing up no the PDF files. No, I have a PDF file here, the curves.pdf, and then for example with Evans, which is able to show you here PDF files, you can just open it and have a look, and you see this is exactly what we have. So basically we have here the curve as a PDF, and the PDF is nice because you know the PDF has basically arbitrary resolution because it's a vector graphics format. So basically you can also zoom in quite nicely. There are no artifacts and so on and so on. So this way you can create PDF files very easily. Okay, good. So basically that's a possibility instead of showing the figure if you do not want to manipulate it interactively. Now let's do a little bit advanced things, and I would like, but the next one I would like to reach is that we have only one axis, like here, x-axis, but it should be in the middle. So I would like to have the x-axis in the middle, and also maybe the y-axis on the right-hand side, so that the numbers are on the here on the right-hand side. And in order to achieve that, now we have to start a little bit with object-oriented programming, or the object-oriented interface of this pyplot package. But it's still not that complicated. And what we have to do is get access to is the so-called axis object. And the axis object is the one which describes how the two axes should be rendered. And we can basically get access, as you have seen on the file, by calling the GCA function, which means get current axis. So basically it would give you the object for the current axis, and then that we store, and then we will manipulate this axis object. Okay, so let's do it. We did the plots, and now we are just basically fetching the axis objects, or we can just before it doesn't really matter, but we will see. Okay, so let's say axis is equal plt dot GCA, get the current axis. And how can I manipulate the axis? You see the example here. For example, if I'm going to make sure that the x-axis, so that the ticks positions are above the x-axis, then here, sorry, if you want to make sure exactly that the ticks are above the x-axis, then you basically say that I want to have the tick position on the top. Okay, so basically I want to have on the top x-axis the ticks. So basically if you look here, we have two x-axes, the bottom x-axis and the top x-axis, and at the bottom x-axis the ticks are always below the axis. On the top x-axis the ticks would be always above the axis because they would be outside. So let's change that as first. So basically we would say I would just execute that so that the AX object knows of what type is, because then I can basically use the auto completion at x-axis. And then what do I want to do? I want to have set ticks positions. So basically set, you see there's a lot of things you can set, but I want to set the ticks positions, and then I want to set it to top. And if you look what happened, so basically the x-axis below is now empty, and the x-axis on the top has now the tick marks, and they are above the axis as we wished. So that's already half of the game, but this is not entirely proper yet, because we also want to make sure that this x-axis, this top x-axis, is not really at the top, but basically here in the middle. And that would be the next thing. We have to set, this is a so-called spine, and we have to set the position of this top spine, and this is exactly the line here. So basically we would say here that we want to pass a tuple which contains, let's just do it. So basically we are saying x upon spines, so basically ax pod spines. So far so good. And then we have to tell which spine we mean. So basically this is the top spine, and then from the top spine we have to tell what do we want to do. And there are not many things, but we can set the ticks positions, and for the ticks positions we have to pass a tuple. And basically the first thing is the data, the string data, which means that the position which we will define here now for the axis should be understood in the coordinate system as defined here. So basically how the data is. We could also specify absolute positions in pixels or something else, but it's not very not very handy here, because we want that here that exactly the spine goes, the axis goes for the 0 point. So we say okay, data, and it should go for the 0 point. And now there is something wrong, as you can see. it says, okay, there is something, spine object has set the x position. That's not the right thing. And if you look at the slides, you see that it's just set positions. That was the wrong thing. It's just set positions. Set positions, and then that's also not the right one. Then it's a set position. Sorry, the S is just too much, I guess. Yep, and now it works. And you see that here, this thing is in the middle. So it's already quite good. But what is disturbing me that here's this thing, I don't want to see it. So basically the other x position, x axis we would like to, the bottom x axis we would like to let vanish. So basically that's the next thing I would like to here achieve. And as you can see here in the examples, the way of doing that is that we are setting the color of the spine just to none, and that would let it vanish. So basically ax, the axis, spine, and then now I'm accessing the bottom spine, and then I say set color, and then I set the color to none, to the string none. And let's see whether it worked out. And you see indeed it worked out. Basically this one is not rendered. And now we have to do the same basically for the y-axis. So basically we want to make sure that the y-axis set x position is set to the right, because we want to have it on the right side. If we execute it, you see that it's fine because the numbers are appearing here. So that's already quite good. We don't want to change the position. This time the position is absolutely fine. It can stay on the right hand side. If we wanted, we can shift it somewhere in the middle or whatever, but for the moment it's fine where it is. And the only thing we want to make sure that the left one basically disappears. So basically we are accessing the y-axis and then we are using set color, and then we are setting it to none. Sorry, this is not exactly correct, because we want to use the spines, and then this is the left spine, and then we want to set the color exactly. So basically the same way as we did here with the bottom, we are doing the same with the left spine, and then setting the color to none, and as you see, it indeed vanished. And with that, basically we achieved what we wanted to have, as it basically this is rendered exactly the same way as shown in the figure. Okay, one nice thing of Matplotlib is the next topic we will try to treat, and that's if you want to treat multiple plots in one figure. So basically maybe an upper plot or a lower plot, or you want to visualize two different data next to each other, and those are maybe in two different kind of coordinate systems, but they are sharing one axis, either the y or the x axis. Then you can position those plots into one plot, and this is the concept of the subplots, and this is exactly what we want to have a look at that now. So basically, also if you follow the slides, you see the subplot is very easy basically to define a subplot. So subplot on the only thing you have to tell pyplot is that you want to make a subplot, and you have to pass 3 arguments. You tell how many subplots you all want to have at the end. So basically it means we want to have a plot containing 2 subplots, and the subplot which we are defining now is the subplot in line 1, column 1. And then we will create a figure, and then we are getting the next subplot. Again, we have still 2 subplots, and now we are providing the plot which is in line or row 1 and column 2. And from that, basically pyplot will automatically know, okay, you want to have the 2 figures next to each other, because I had all together 2 plots, and the first one is in the 1-1 position, and the second one in the 1-2 position. So basically they should be next to each other. If you would turn the second one in 2-1, then it would automatically basically put it below each other. So this is very simple, and then let's have a look at that. So basically we will just say plt.subplot, and then we are saying 2 by 1 by 1, 2 by 1, so that we have 2 subplots, and this is subplot 1-1, and we're just plotting whatever we wish to plot. So basically plt.plot, and just let's just plot the x and the y functions, the cosine, and then we are making the second subplot. and that should be again we have two subplots all together, and it's on position 1, 2, so first row, second column, and here we are basically plotting the other function x and y2. And if you execute that, then you see that basically at the end what we got, okay, we could here was add to plot.show, just to make sure that if you get the same piece of code in somewhere else than in a script than it shown, and then you see that basically we get two subplots, they are below each other, and here you see that here you have the cosine and the sine curve. Right, so it's quite flexible, and you can have any number of subplots. The only thing you have to care about is that you have to specify at the beginning the right number of subplots and then the positions. Also, you can have certain subplots which are spanning more cells and less cells. I mean, this is the subplot command is very, very versatile, and you can just look up for the fine details, the documentation. The last thing which I would like to show you is when you have axis. And or almost the last thing I would like to show you, when you have axis, you can also use tech commands in order to label the axis, and that's also very, very handy. I find, for example, let's assume we just want to make a plot. I make a new linspace, and basically I will run only for from 2 to 2 pi. So basically starting from 0 to 2 pi, and let's say let's take 100 points, and then I want to have just one function, the y function, which should be, let's take the cosine of x, just to keep it simple. And now we would like to plot it, so that's the definition. Oh, something is wrong. Yes, because pi is an unknown constant, but I want to use the pi within the numpy module, and then everything is fine. Okay. And now what I would like to do is to plot this thing. Of course, I have to use the plot from the PLT package, and then x and y. And of course, it would be quite nice, especially if you are plotting trigonometrical function. It could make sense to make the axis such that here I have 0, then I have here maybe here pi, right? Then I could have here pi half and 3 pi half and maybe 2 pi as on the axis, right? Because it's much better to have an axis which shows you that that thing in the multiples of pi. And basically that you can access with the xtix command. And the xtix commands you can pass either one argument which tells you where the tix should be, and that should be exactly on the position pi and 2 pi and so on and so on. And basically we could even generate that. If you think about that, we could just say here xtick pause, and then we could just use linspace in order to create it. So basically we would like to go from 0 to 2 pi as before, and then let's make just all together 0, pi half, pi, 3 pi half, and basically 2 pi, so basically 5 positions. And if we just okay, nothing changed of course, but if you look at the xtick of the array xtick positions, then you see that basically it has exactly the right values. And now I could basically tell the program to use those positions as ticks, so basically as marks, and basically the command is, as you see on the slide, xticks, and then I will now just specify xtick pause as an array. And if you look at that, that looks already quite good. It's exactly the right spot, right spots and the interesting spots. But of course the numbers are horrible. I mean, this is would be much nicer if we would have if they would have proper names. And basically we can just make another array. Let's say xtick names, and here we are just providing the names in LaTeX as LaTeX commands. For example, here we would have for the first, okay, we can just have the 0, and then the next one is pi half. The next position would be pi half, and that you can enter here as a LaTeX frac, and as because it will be basically a fraction, and then the LaTeX command pi over 2, and then you just close the mathematical mode. And then the next one would be just pi. So this is basically the command pi, the mathematical command pi in tech, and then the next one would be 3 pi over 2, So basically I will just copy this here. Of course it should be quoted, and it's 3 pi over 2 here, and then the last one I will just say is 2. It's 2 times pi, and of course it should be also in mathematical mode. So basically you can insert Python in that way. This won't work yet probably, and I will show you in a second why. But basically let's pass these xtick names as a second argument. So basically here as a second argument I would just pass xtick names. And oh yes, there's a problem. There's a problem in parsing this text which I had done, and the reason for that is, and I will show you in a second how to, or I will show first how to fix it. I will just write R here before the string, and the explanation follows in a second. Just let's see whether this works at all. And voila, it seems to work now. And you see I have exactly 0, pi half, pi, 3 pi half, and 2 pi. Maybe 3 or 3 half pi would be nicer. So basically I will just do it differently. I will just here write 3 half times pi, and then probably it looks even better. Now the big question is why this didn't work out the first time without putting this R here, or what this R is. And the problem is that the basic problem which we have is that if you have a backslash, you know yourself, a backslash has a special meaning in Python. For example, you remember if I have a string which has a backslash nb, and I just print it, then this backslash n means nothing else that this is a new line. So it's a special for control character, it means a new line. The problem is that Python also tries to interpret those things as special characters, right? So there's this backslash f and this backslash p, and you would like to make sure that Python doesn't do that. And in order to make sure that Python doesn't do that, one way of doing this is basically writing a double backslash. So basically if I'm here doubling the backslash and executing it again, then it indeed, the backslash no means the literal backslash character, so Python doesn't try to associate a name, a special meaning with that, and then the character n. So it's not the special character backslash n anymore. And this is exactly the thing which you have to reach it here. But the problem is what you would have to do then to double every backslash. So basically that would be a possibility. And you see, that works again, but it can become a nightmare because it's much more difficult to read. And the solution, what you can do is you write an R in the front, which means row string, and that means that tells Python whatever follows in this string, do not try to interpret the backslash as a special prefix is, but always backslash means always the literal backslash, and then it works out quite nicely. Just to bring you an example here, if I would have that's AB with the backslash n as a new line character, but if I make a row string out of that, then basically it means the literal backslash and the literal n character. So it's not converted to special characters, and therefore you need the R. And this R is very, very handy if you are passing commands to languages which uses the backslash for something. For example, if you want to enter dash commands within Matplotlib. And as I said, the nice thing is you can use most of the LaTeX constructs, the simple LaTeX constructs in those things. So basically you can format your axis or legends the way you would like to have it. So it's quite nice. And basically with that, I have shown you all the basics, what you need to know in order to start the exercises. There are a few more things here which I listed it, but basically there are so many that I definitely cannot cover all of them. Also, there's a very, very, very good tutorial in the internet, and basically I added the link here. This is the Matplotlib plotting section in the SciP lectures, and I would like to ask, and this is also part of the exercise, to basically go through the plots there and basically do all the plots and try to understand how they are generated. It's a very, very good introduction. It's much better, which I could set it up, so there's no reason to that I'm just duplicating it. Just go through that, and basically if you go through that lecture, through that chapter, and you are typing in all the examples yourself, and you make sure you do it step by step, so you make sure you understand all the commands which are there and why the resulting figure looks as it does, then basically you will reach a very, very high level of plotting capabilities in Python. And although this is connected to some kind of programming, you basically, there is no limit how you can configure the plottings in Python, and especially if you have to create figures in a batch. So basically for many data you always have to do the same steps in order to create the figure. Then in Python you can automate it very, very nicely, and then you can just run your Python script for the different data sets, and all the steps which you do usually by hand by clicking around in some software, Python can do that for you if you basically wrote the appropriate program for that. And with that, basically, I would like to end this short session. I hope that you had fun, and I hope you will have a lot of fun when plotting your scientific data using Python. And yeah, thank you very much for your attention, and I hope to see you in the next session. Take care. Bye bye.